Welcome to the flight simulation. Look at this quadcopter resting in midair. In a calm environment, it looks perfectly still, as if it's supported by an invisible shelf. That stillness is a calculated effort. Every aircraft is caught in a continuous tug-of-war between four aerodynamic forces. To hover, the downward pull of gravity must be perfectly counteracted by the aerodynamic lift and mechanical thrust of spinning blades. A hovering quadcopter is essentially an aircraft in a constant state of falling. It remains airborne only because it is violently shoving massive quantities of air downward to fight the Earth's pull. It is a fragile equilibrium, easily shattered by a change in the environment. A sudden, violent gust of wind slams into the frame. The equilibrium breaks. The drone banks sharply to the left, and gravity begins to pull the aircraft toward the dirt. Freeze right there. Relying on human reflexes to save this aircraft is impossible. The average human reaction time is roughly 250 milliseconds, far too slow to prevent a crash from this altitude. To survive, the onboard computer must sense the shift, calculate a solution, and execute a physical correction in less than 1/100th of a second. The clock starts now. We are at T plus 0.001 seconds. The flight controller, the drone's brain, must identify how the drone's orientation has changed. It queries the Inertial Measurement Unit, or IMU. This sensor acts as the drone's inner ear, perceiving its position in three-dimensional space. Inside this chip is a micro-electromechanical system. It is a microscopic piece of silicon vibrating back and forth at an ultra-high frequency. When the wind tilts the drone, the Coriolis force causes that moving mass to deflect slightly sideways against its electrical housing. The chip measures a minute change in electrical capacitance from that deflection, instantly sending a digital alert to the brain, tilt detected, 5 degrees left. At T plus 0.002 seconds, the brain has the data, but adding power blindly would likely cause the drone to violently overcorrect and flip in the opposite direction. The flight controller processes this data through an algorithm called the PID loop, proportional, integral, and derivative. Each stream performs a different calculation to find the exact power required. The proportional term handles the present error. It calls for an immediate spike in power to the left motors to counteract the tilt of the wind. The derivative term predicts the future rate of change. It acts as a dampener, easing the motor power just before the drone levels out to prevent the aircraft from wobbling or oscillating. In a fraction of a millisecond, the flight controller has converted a physical crisis into a solved mathematical equation. By T plus 0.003 seconds, the digital command travels to the electronic speed controllers, or ESCs. These are the system's muscles. The ESCs open their electronic gates, allowing a massive surge of current to flow from the battery into the motors. Electricity floods the stator coils, creating electromagnetism that spools the propellers to 10,000 revolutions per minute instantly. This sequence has translated a microscopic vibration into digital math, and finally into enough mechanical force to fight the wind. Resume time. At T plus 0.010 seconds, the left propellers bite into the air, and the drone snaps to a level hover. This entire chain of sensing, calculating, and firing electricity occurred faster than a human could blink. The flight controller maintains this stability through extreme frequency, repeating this entire measure, calculate, adjust sequence 8,000 times every single second. Remaining airborne is the result of this high-speed, invisible interaction between advanced physics and computer code. Without these microscopic adjustments, the quadcopter is simply a collection of carbon fiber and silicon falling to the Earth. The drone is safe and balanced, but it is currently flying blind. While the IMU maintains its posture, the aircraft has no awareness of its actual location in the world. To navigate autonomously, the drone needs eyes. In your next briefing, we will explore the extended Kalman filter and how it fuses multiple sensors to map reality. End transmission.